All right, so today I'm gonna explain another important video. So this is a new playlist normalizing flows and diffusion. So most of the time I will be talking about diffusion, but I also talk about diffusion bridge, flow matching, uh, even normalizing flows and hierarchical variational autoencoder, a little bit about Langevin dynamics, a little bit about denoising score matching. These ideas, denoising, score matching, and flow matching, are very important, and they are also related to diffusion. You may say this is deterministic, but you will see that how it will be related to diffusion as well. So in the next 200 videos, I try to cover mostly this diffusion, and my concern is mostly graph generation and language, because these are combinatorial. Computer vision is very easy. The diffusion is almost solved. Of course, there are some still computational complexity is high, but the field of diffusion-based graph generation and also diffusion LLM is not mature in comparison to computer vision. So I focus on graph applications rather than image application, which is very easy. So this paper in 2021 in NeurIPS is really interesting. So the algorithm consists of two neural stochastic differential equations, a forward SDE that gradually adds noise to the data to transform the data into Gaussian random noise, and a backward SDE that gradually removes the noise to sample from data distribution. By jointly training two neural SDEs to minimize a common cost function that quantifies the difference between the two, the backward SDE converges to a diffusion process that starts with a Gaussian distribution and ends with the desired data distribution. Our method is closely related to normalizing flow. The problem of normalizing flow is that Jacobian is computation expensive. That's why people talk about diffusion and flow matching, and even implicit neural representation. These are new paradigms rather than the old paradigms of normalizing flow. So here you see a comparison of diffusion models and normalizing flows. In normalizing flow, both the forward and the backward process are deterministic. Even in flow matching, everything is deterministic. But they are inverse of each other and thus collapse into a single process in normalizing flow. The diffusion process has a fixed forward process and trainable. Of course, even the forward can be learned. But here you see in this picture, you see the diffusion has a fixed forward process and a trainable backward process. Both are stochastic. In diffflow, the model of this paper, both the forward and backward are trainable and stochastic. That's why they call normalizing, diffusion normalizing. So they want to bridge the gap between these two ideas of diffusion and normalizing flows. So they are trained, the forward and backward process are trained simultaneously by minimizing the distance between the forward and backward process using that KL divergence. This cost turns to be equivalent to the negative elbow, we call it. But one advantage to use KL divergence directly is that it can be estimated with no bias using sample trajectories of the diffusion process. The KL divergence in the trajectory space also bounds the KL divergence of the marginals, providing an alternative method to bound the likelihood. So, in normalizing flow, But our problem is like a time series, a trajectory. It could be anything. You can use images, time series, graphs, languages. You can use anything for normalizing flow. But let's see that the trajectory in normalizing flow, we always model it by a differential equation. You can do it for many benefits. This differential equation starts from random and ends at z. So the probability distribution of x is this, and under mild assumption, it evolves. So we know the evolution of this probability distribution that starts from random x. We know it. So we can compute the likelihood of the model at any point and any data point. In the discrete time setting, the map from x to z in normalizing flows is a composition of collection of bijective functions. The trajectory satisfies this, and similar to equation 2, similar to this equation, based on the rule for change of variable, the likelihood of any data sample can be evaluated. So we just use the rule for change of variable, that this determinant of Jacobian appears. And you know about diffusion models, the forward, you model it with STE. Of course, for graphs, people say, oh, we don't know the intermediate, if it is valid, for example, molecule at each of the intermediate states. But there are ways to handle that as well. And this is the backward diffusion that, if you are familiar with score matching, we call this S, the score network. Because it's just because S it coincides with the gradient of your probability of forward here. So in the discrete setting, the trajectory distribution can be written like this. And you know the KL divergence between forward and backward. So what is this diffusion normalizing flow? Now we want to make the intersection of these two paradigms. So similar to diffusion models, the diff flow models also has a forward process. So the backward process is here. So it's very similar to diffusion until now. The major difference is that instead of being a fixed linear function, as in diffusion models, the term, this drift, look at this F drift, is learnable in diff flow. The forward processing initialized with data samples at t equal to 0 and t at noise. So our goal is to ensure distribution of the backward process is close to the real data distribution. That is, we would like the difference between backward and forward for the initial to be small. To this end, we use KL divergence between the backward and forward probability over the trajectory space as a training objective function. But in implementation, first we discretize the forward, and because we work on computers, here we have dropped the dependence on the parameter theta to simplify the notation. So we can see how KL divergence between the forward and backward look like. There are three terms. You see these three terms in almost all papers in diffusion-based generation. The term L0 is just a constant. We don't need that. Determined by entropy of data set. The last term is easy to calculate because P of xn is a simple distribution. For example, Gaussian distribution. So we can calculate it. But this Gaussian distribution is not easy in discrete method problems like graphs and language, because you need to go from Gaussian to categorical distribution. So that's why I say when you go from image applications, image generation, to graph generation and language, things doesn't work as it worked on images, because you have a combinatorial problems. And even a graph, the nature of that, this data structure, at intermediate states, it should have a symmetric matrix. It should be valid. Your molecules that are generated should be valid. So you have many problems that you don't see it even in images. Images looks continuous, but graphs and language look discrete and combinatorial. So to evaluate L from 1 to n, you see I from 1 to n minus 1. To evaluate that, we estimate it over sample trajectory from the forward process. So for a given trajectory sampled from forward, we need to calculate the backward along the same trajectory. To this end, a specific group of delta is chosen such that the same trajectory can be reconstructed from the backward process. So since delta is a Gaussian noise, the negative log likelihood is equal to this after dropping the constants. So this 13, this that you see in our papers, this 13 is equivalent to just minimizing the falling loss. Now it is very much simplified because of as I said, because of its Gaussian and many simplifications. And you see here the gradient flow chart. In the training, you have real data distribution. You sample delta from normal Gaussian, and then you sample tau. Then you can get your gradient descent step. For stochastic adjoint algorithm for diff flow, you are given the forward trajectory. You go through these updates. So one challenge in training diff flow is memory consumption. When a naive backpropagation strategy is used, the memory consumption explodes quickly. Indeed, differentiating through the operations of the forward pass requires unrolling networks n times and catching all network intermediate values for every step, which prevents this naive implementation of diff flow from being applied in high-dimensional applications. So inspired by this adjoint method that we use in neural ODE, we propose the adjoint variable and a stochastic adjoint algorithm that allows training diff flow model with reduced memory consumption. So this adjoint variable is very good for reducing the memory consumption. So we can use, we note another similar approach of training STEs caches random noise and further takes advantage of pseudo-random generator to save memory. So this is time discretization and progressive training. They propose two time discretization schemes. And here you see illustration of forward trajectories of diff flow, DTPM, FF Jord, and each row shows two trajectories of transforming data distributions. The forward module of diff flow is a combination of normalizing flow and diffusion models. And they did experiments on, so this is the proof of theorem 1 that normalizing flow is just a special case of diff flow. We show that minimizing the KL divergence between trajectory distribution is equivalent to minimizing negative log likelihood in normalizing flow. The derivation is essentially the same as in this reference 42, except that our model is for density estimation instead of sampling. So you see samples on 2D data sets. All three models have reasonable performance on data sets that have smooth underlying distributions, but only diff flow is capable to capture these complex patterns. You know, this diff flow can capture these complex patterns like this fractal tree or Sierpinski carpet. Also, they worked on C410 and MNIST, which are easier. And they compared, for example, diff flow with ODE to DDPM, which is classic. While diff flow gains more flexibility due to introduction of a learnable forward process, it loses the analytical form for P and thus the training less efficient compared with score-based loss. Training diff flow relies on backpropagation through trajectories and is thus significantly slower than diffusion models with affine drift. So diff flow is about 6 times slower than DTPM.